Good morning to all. Today I am going to discuss the Compton effect. It is a continuation of the previous lecture. In the previous lecture, I have already detailed about the derivation of Compton effect. In this lecture, I am going to discuss some important other aspects of the Compton effect, in which I try to discuss the direction of recoil electron, kinetic energy of the recoil electron, which are the important to understand. Now let us start. First of all, I am going to discuss the value of Compton shift. The Compton shift, rather Compton shift, Compton wavelength, lambda c. Lambda c is computed with the standard value of h, mass of the electron, and the speed of light. Substituting the standard values, we get the value of lambda c is equal to 0.024271 angstrom. Now, summarizing the previous result as a in the form of table, the angle of scattering and the Compton shift and the value of the scattered radiation wavelength, value of the scattered radiation wavelength. If theta is 0, angle of scattering is 0, delta lambda is 0, so lambda dash must be equal to lambda. Whereas theta is pi by 2, it becomes lambda c. So the scattered wavelength is lambda is equal to lambda plus delta lambda. And the pi is, if the theta is pi, that is called backward scattering. The Compton shift is 2 lambda c, and that's the scatter wavelength is lambda dash equals to 2 lambda c plus lambda. That is the now I'm going to discuss the kinetic energy of the recoil electron. What is the kinetic energy of the recoil electron? If you look at that, the kinetic energy of the recoil electron is considered as the energy being lost in the process of scattering is given to the electron, that is called the kinetic energy of the recoil electron. So kinetic energy of the recoil electron is mathematically defined as equal to E minus E dash, the energy difference between the incident and the scattered. Substituting the standard values, we get the kinetic energy expression as the Ke equals to hc upon lambda, a big bracket, lambda c into 1 minus cos of theta over the lambda plus lambda c bracket 1 minus cos of theta, and big bracket is closed. With the help of the theta for different value of the 0 and pi by 2 and pi, substituting in the expression, we get the change in the energy, that is kinetic energy of the system, is equal to these one. So we try to calculate the fractional change in the energy, that is delta E by E, that is lambda c1 minus cos of theta, lambda plus lambda c1 minus cos of theta. After making the substitutions, let alpha is equal to lambda c by lambda, we get an expression that is this one, which can be further resolved using 1 minus cos theta is equal to 2 sin square theta by 2, it gives you the final expression, that is the fractional loss in the process of Compton scattering. Delta E over E is equal to 2 alpha sine square theta by 2, 1 plus 2 alpha sine square theta. Similarly, the direction of recoil can also be computed with the help of the equation 2c and 2d. I have discussed these equations in the previous lecture. Tan phi is the angle of direction of recoil electron, sin phi by cos phi, and it will give you a final expression, that is tan phi equals to lambda bracket lambda over lambda plus lambda c cos of theta by 2. Under the certain value of the theta, we are able to compute the value of phi. If theta equals to 0, then we have phi is equal to pi by 2. If theta is equal to pi, we have the phi is equal to 0. Now, I'm going to discuss the two important questions which is asked and very important to understand. Why do we have incident wavelength in non-zero scattering angle? As we know, the incident wavelength is available in the direction of theta is equal to 0, that is angle of scattering. But for non-zero value of theta, we have incident wavelength, because delta lambda equals to lambda c1 minus cos of theta. If theta is non-zero, so cos of theta is also non-zero, not equal to 1. So therefore 1 minus cos of theta is equal to not equal to 0. Therefore delta lambda has to 0 only when the lambda c must tends to 0, because 1 minus cos theta could not be 0 for non-zero value of theta. If lambda c tends to 0, it means that the lambda c, that is Compton wavelength, h upon m naught c, where c can't be infinity, h can't be 0. Only the parameter which makes c is equal to 0, that is mass, should be infinite. It could be possible if the mass is attached to the atom system, means the electron is not free. Therefore, you can say the scattering takes place by the bound electron, the atom, or you can say atom as whole. So the Compton shift will be 0, and therefore lambda dash must be equal to lambda. That is the reason why we are getting a value of the lambda in the direction of the non-zero value of theta. Now, the another important question is, why do not observe the Compton effect by the visible light? As we know, the Compton shift is independent of the incident wavelength and also independent of the material, but dependent on the angle of scattering. So we have the maximum change in the Compton shift is delta lambda at the angle of pi, that is backward scattering. So delta lambda must be equal to the order of the 0.5, and therefore we calculate the relative change in the Compton value, that is the delta lambda over lambda dash. For the fixed value of delta lambda, lambda is increasing, capital R is decreasing. For a visible range, the wavelength of the light ranging from 4000 to 8000, the lambda average is 6000, and taking the value, and the value of R is 10 to the power minus 6, which is very small. So we can say that the Compton shift